Happy Chapter 5.
Chapter 5.
So much fun.
Chapter 5. If you love triangles, it's still talking about triangles, relationships, and triangles. Ooh, how exciting. Okay, as a warm-up, I had them write down what they learned in Chapter 4, and now we're going to do a little share. Who wants to share? Matthew?
How to write proofs for
How to write proofs for triangles. So many different ways. 2-column, flow, paragraph, technically coordinate proofs. Okay, let's get at least 2 other shares. Gwen?
Angle bisectors.
Angle bisectors. Gwen, we're going to talk about angle bisectors today.
Oh my gosh.
I learned SAS.
SAS.
I want to say
You learned Matthew has a dirty mouth. All right, good. Thanks for sharing. So today we have 2 big theorems we're going to talk about. And yes, if you looked at your outline, 5.1 is really long. So we're splitting it like into 2 notes days, 5.1a and 5.1b. So today's 5.1a, and then you have tomorrow as a work day and Friday as a work day on a couple worksheets because it just kind of takes practice. Okay? So first, we have to review over some vocab that we already know, hopefully. So in these boxes, I want you to jog your cute little brains. Cute big brains.
Wrinkly things.
And you can either write out in words what these are, or you can draw me a picture. All right, I'm giving you 1 minute. You have 3. Perpendicular lines, segment bisector, perpendicular bisector. You can just draw it if you want, yeah. Okay. Who can tell me what Who can tell me what perpendicular lines are? Oops. Perpendicular lines. Gwen.
Lines that intersect in a 90-degree angle.
Oh, beautifully said. Lines that intersect at a 90-degree angles. How do we mark that? Little box. What do we call 90-degree angles?
Right.
Right angle. Nice. Okay, we know what oh my gosh. You threw me off now.
English.
I keep wanting to say parallel. It's been a long day. We know what perpendicular lines are. Lines that intersect at a 90-degree angle. Do we know what a segment bisector is? Ooh, Alex, I like it. She was fast with the hand.
It's when there's a line that goes between another line and it makes a group.
Ooh, okay. I'm going to draw what you just said. So I'm going to draw a segment. And she said a line that goes through it. And it makes what congruent? Alex, it makes what congruent?
A and B. The 2 lines.
These 2?
Yeah.
Meaning it passes through what point? The midpoint, right? If it bisects it, it goes right through the midpoint. Good. So this could be a point, it could be a ray, it could be a line. That intersects intersects a line segment at its midpoint. Or basically like what Alex said, it like splits it into two congruent parts. That's what a bisector is. Okay, so knowing what we know about that, and we actually have talked about perpendicular bisectors very briefly, like way back in chapter 1. We know what perpendicular means, and we know what a bisector is. So what do we think a perpendicular bisector is? Alejandro?
A line that intersects another line at a 90-degree angle and hits the midpoint.
Couldn't have said it better myself. It not only hits the midpoint, it not only bisects it, but it intersects it at what degree angle? 90. It fits both criteria. It's perpendicular and it bisects. So, nice job. A line or a segment perpendicular, I'm going to use that notation, perpendicular to a segment that passes through the midpoint. Of the segment. Okay. So today, our first theorem is called the perpendicular bisector theorem. You don't have to write all that down. If you can draw a picture and you know what that means, that's fine. That's just a little refresher. Here's our new theorem for today. If we have a point that lies on a perpendicular bisector, so let's look at this example. You can see I have line segment AB. Ignore the fact that this looks like a triangle for a second. Ignore that. I have line segment AB. CD is perpendicular and bisects line AB, right? We can see that. If that's true, this is what this theorem says, then point C is equidistant. Do you guys know what that word means? The same distance, equal, same, equal. The same distance from each endpoint of the line segment. So this distance from C to A would be the exact same distance as the line from C to B, that endpoint. That's always going to hold true if it's a perpendicular bisector. If it's just a normal bisector, that might not always be, oh, I guess I could go to the endpoint. That's not always going to be true. It has to be a perpendicular bisector. I found this nice visuals on Desmos. You want to see it? All right. So here we have segment CU. There's no markings that these are congruent, but I'm telling you they are. So I have this bisector and they're showing you the perpendicular bisector, right angle here. Let's see if I can make this easier to see. There we go. So if I find the distance between a point here and the end points, no matter where point E is on the segment, on the perpendicular bisector, can you see that those lengths look like they'll always be the same? Okay, that's what this theorem is. It's true. These will always be the same if it's perpendicular and if it bisects, crosses at its midpoint. Okay, there's our first. Oh no, I read it. There's our first theorem for today. So in this picture, if CD, line CD, is a perpendicular bisector of AB, then that length AC is going to be the same as length BC. Those lengths, distances are going to be the same. Okay, there's our first theorem. Now, its converse also holds true. You know what converse is? We just flip-flop the hypothesis to the conclusion. So if we have a point on the perpendicular bisector that we know these distances are equal, if we know, in this case, AE is equal to BE, then we know for sure point E is on the perpendicular bisector. I'm gonna put lies on. Okay. So we can also use that in the converse. If we know it's like equidistance, then we know that that point is on the perpendicular bisector. All right, here's what I want you to jot. You have a little bit of room under these boxes. Here's what I want you to jot down in your notes. Because on your homework, it's going to say, conclude whether this is indeed a perpendicular bisector. If so, find this. Like, using the given information, explain what allows you to conclude it is a perpendicular bisector. So in order to do that, you have to show two things. So to conclude a point lies on a perpendicular bisector. And I'll walk you through this, like I'll model it as we go through example problems. You have to show two things. One, you have to show that the segments are perpendicular to each other, meaning they form 90-degree angles. So there'll be some marking showing you that they are perpendicular to each other. The second thing you have to show depends on if you're going to use the converse or like the original theorem. So if you're going to use the original, you have to show that it bisects the segment, or you could say intersects at midpoint. Or if you want to use the converse, or the point is equidistance, like these lengths are the same from segment endpoints. And then we can use the converse. Okay, so jot that down. That's basically what we're going to do each time we do one of these problems. I'll kind of like I said, like verbally model. First of all, do we even know if this is a perpendicular bisector? Or do we even know that this point is on the perpendicular bisector? Luckily, with markings in geometry, these are easy to detect. Okay. You guys ready to try one?
Sure.
You're like, what else are we going to do? Okay, good, Malin? All right, so this says find the length of BC. I'm going to highlight that in green. They want me to find this length. So right now, again, kind of ignore it's a triangle. Right now, I see I have line segment A, B, and I have this dashed line passing through that segment. First, how do we know that that line is a perpendicular bisector? It has a right angle, so that meets the first criteria. So first, we see that AB, the segments are perpendicular to each other. I guess DC is technically not a segment, it's a line. We know they're perpendicular. Okay, first kind of piece is met. They have to obviously be perpendicular in order to be a perpendicular bisector. Second, how else do we know this is a bisector? It splits it into two congruent parts, or it intersects at its midpoint. We would say AD is congruent to DB. Okay, that's what you would write on your homework. It says, like, tell what information lets you conclude it's a perpendicular bisector. There you go. It's perpendicular and it bisects. Meets both definitions of a perpendicular bisector. So, to use the perpendicular bisector theorem, our hypothesis is met. We know it's a perpendicular bisector, so we can conclude that that point, in this case point C, is equidistant from A than it is to B. Meaning if this distance is 8.5, what's this distance going to be? That's a perpendicular bisector theorem. Okay, let's try another one. Tell whether you can conclude that point Q lies on the perpendicular bisector of SQ. Then find PQ. All right, so point Q is that lying on a perpendicular bisector. So here I have segment PR, and this dashed line is asking you, is this a perpendicular bisector? Oh, are there markings here? I think I accidentally erased them last hour. I don't know how I did it, but I think I accidentally got rid of them. Okay. So, first, are they perpendicular to each other? Yes, beautiful. Second, is it a bisector? Yep, it's showing me it's intersecting at its midpoint. SR is congruent to SP. So my answer to the first question is yes. Yes, we can conclude that it is a perpendicular bisector. So the theorem tells us that Q is equidistant from P, one endpoint of the segment, than it is to R, the other end. If we know those are equidistant, how would I set up an equation to solve this for X? I know they're equal. Matthew?
3x plus 1 equals 5x squared.
Thank you. Solve for X, hashtag algebra. Do you guys still say hashtag stuff?
It depends on the day.
Gwen says yes, so that's cool. All right, X is 2. Tech, were the directions asked me to find X or find something else?
You are supposed to, actually, you don't have to find it.
What does it tell me to find?
PQ.
I need to find PQ. That's what they're asking me for, that length. Well, we know PQ is 3 times X plus 1. And now we know X is 2. So that's going to help me find PQ. PQ is 7. What would my units be on this? Units. We're talking about a length. We're not talking about an angle. Don't put degrees on a length measure. Here's something to be careful. That's why I put them in red. Careful. Don't assume that these triangles are equilateral. Okay? When you're looking at this as a triangle. Just because these two sides are congruent, you don't necessarily know that that's equilateral. So don't assume that. Also, don't assume all perpendicular lines are necessarily bisectors. All right, so take a look at this one. This one says, tell whether you conclude that point W lies on the perpendicular bisector WY. I see it's perpendicular to this segment, but what piece am I missing here to make it a perpendicular bisector? What's not congruent? Right? There's no marking showing me that it's bisecting it, that it's splitting that segment in half. They're telling me this is 6. If they wrote a 6 here, it'd be like, oh, yep, those are congruent. It's a perpendicular bisector. So in this case scenario, it's kind of like a non-example. This would be no. We can't conclude that's a perpendicular bisector. There's no markings that, and this is what Gwen said, that XY is congruent to YZ. Now, if we wanted to use the converse, if they would have told me that point W is equidistant from X as it is to Z, if they would have shown me this, then we could have used the converse, saying like, oh, they're equidistant, meaning that it does lie on the perpendicular bisector. So add in, or there's no markings that WX is congruent to WZ in order for us to use the converse. Showing that they're equidistant. Okay, that's our first theorem for today. Perpendicular bisector theorem. Ready for the next one? All right, first let's review over what an angle bisector is. So in this box, I want you to draw or explain in words, whatever you want to do, an example of an angle bisector. You don't have to draw a triangle. Nice! Okay, what markings would show the bisector? Nice, Lauren. All right, who can explain this? Here's my angle. I just draw a random one. What's an angle bisector? Lauren, you explain it. You did it perfectly.
All right. I don't know.
Yeah, just tell me what you
I
did.
just drew like a circle thing in a line. I don't know.
Okay, but where did you draw your line?
Through the middle of it.
Good, through the middle, because what does it do to this angle?
Splits it in half.
You know that. Splits it into two congruent angles. That's exactly what an angle bisector is. We know what a segment bisector is. It splits the segment into congruent segments. So an angle bisector, remember when I gave you guys this spiel? I was livid that you didn't get this right on the quiz. Remember? I was like, angle bisector. We know what this is. It splits the angle into two congruent angles. So if you want to write it in words, a ray or line segment that divides an angle into two congruent angles. Okay. So here's our next theorem. It's called the angle bisector theorem. Pretty clever, huh? Here's how it goes. If you have an angle bisector and you have some point that's on the angle bisector, they are equidistant from the sides of the angles. Okay. Do you guys remember way back in chapter 3 at the end where I did those really long problems where I gave you a point and then two other points and I said, what's the shortest distance from this point to the line? And you had to calculate like those 4 steps. Don't worry, we're not doing that. But you found the line perpendicular from the point to the line that connected the other 2 points. Remember doing that, kind of? The shortest distance is always a perpendicular distance. So they're showing you here, well, first of all, we have a bisector, right? Because of this. Angle bisector. BF, ray BF is bisecting that angle. So the shortest distance, which would be the distance perpendicular to each sides of the angle, are always going to be congruent if it's on the angle bisector. I don't have a nice visual for this, but you can kind of picture this. If I like slid point F up here and drew in the shortest distance, the perpendicular distance, doesn't it look like those could be also the same, equidistant? Okay, that's what this theorem is saying. So let's write it out in words. If ray BF bisects angle DBE, and you also have to show that these are perpendicular, meaning we're looking at the shortest distance. If FD is perpendicular to both sides of the angle, BD and FE is perpendicular to ray BE. Okay, that's kind of your hypothesis. If it splits the angle in half, and if we're looking at the shortest distances from each side, then those distances are going to be the same. Then FD is going to equal FE. So the converse of this one also holds true. If you know this point is equidistant from the two sides, and it's looking at the shortest distance, the perpendicular distance, then we know that point has to be on the angle bisector. So then we like know that that ray does indeed bisect the angle. So if, here's the hypothesis for this one, you just flip-flop this. If we still have to show that they're perpendicular, FD is perpendicular to BD, and FE perpendicular to BE. And we know those are equidistant. Then we can conclude BF bisects the angle. Then we can conclude this, that those two angles are the same. Okay. You don't really have to like know, guys, like which one you're using. You just have to like recognize this, like, oh, hey, I see that those are equidistant, so those angles are going to be the same. It does bisect that. So in order to conclude, I'd write this at the bottom. I know we don't have a whole lot of room, but to conclude, a point lies on an angle bisector. These are the two things you have to show for this theorem. First, you have to show the bisector is perpendicular to each side of the angle, each angle side. Okay, this only works if we're looking at the shortest distance. Because obviously you could say, oh, I found a counterexample here. Point F, if I drew it way over here, that's obviously not the same distance as this. So we're saying, okay, well, we're just taking the shortest distance, the distance perpendicular. So that has to be like shown, or that has to hold true. And then you have to show either that it bisects the angle, and we can use a theorem, or that those are equidistant, and then we can use the converse. Okay. So angle bisector markings or to use the converse, point is equidistant. Sorry, I know I didn't give you a lot of room to write this. From angle sides. And then we can use the converse. Okay, does that kind of make sense? We'll do a couple examples. Okay. Got it. So, tell whether you conclude that WY is indeed the angle bisector of XYZ. So here's angle XYZ. Can we conclude that, why would they say WY? That's so weird. YW, ray YW. Can we conclude that it is an angle bisector? Okay, first things first, we have to make sure that we are looking at the shortest distance when we're looking at point W, the shortest distance to the two sides, aka the perpendicular distance. So that's like the first thing is we do have to show that that distance, like WX, is perpendicular to each side. And WZ is perpendicular to the other side. Okay, so that's what you have to look at first. Make sure they're looking at the shortest distance. Then in order to conclude, we have an angle bisector here. It either has to have markings that it's bisecting the angle. Do I have markings that it's bisecting the angle here? No. So I'm like, I might be using the converse here if they're showing me these are equidistant. And they are. So the second thing is that, hey, these are equal distances. Or you can say those like segments are congruent. So this is using the converse, that those angles are indeed going to be congruent because this point lies on the angle bisector. Okay, that's that theorem. So what would the measure of angle WYZ be? Well, this is 28. It's the bisector. This is also going to be 28 degrees. Yep. Okay, not too bad. Let's try another one. I drew in something for you. All right, this one. Tell whether you can conclude that PS is the angle bisector of angle QPR. Then find QS. All right, so we got QPR here. Is that indeed the angle bisector? Yeah, it's showing me it bisects it, right? And it's also showing me, if I'm looking at these distances, we're looking at the shortest. So both of those like criteria are met. Hey, SQ is perpendicular to PQ. And SR, it's okay if I'm reading these letters. SR is perpendicular to PR, ray PR. And they like literally showed me that it bisects the angle, that angle QPS is congruent to angle SPR. So my answer is yes. I don't know if we wrote yes on the last one, but I would write like yes, we can, because it says tell whether you can conclude. Sorry, it's usually an answer like yes or no. Yes, we can conclude it's a bisector. Now, folks, if these markings weren't here, that perpendicular, just because it had the bisecting markings, wouldn't be enough information to say, to find, I guess, to more find. We could say it's still a bisector, but that wouldn't allow us to conclude that these are equal to each other because we don't know if we're looking at the perpendicular distance or the shortest distance. Okay, so this is kind of using like the actual angle bisector theorem. We know it's an angle bisector, and we know we're looking at the shortest distance, so we know they are the same distance. They're equidistance. So I set up my equation by just setting them equal to each other. Solve for x. X is 3. They didn't ask me to find x. They asked me to find PQ. No, they asked me to find QS. PQ is QS. They asked me to find QS. QS is 4x minus 1. X is 3. QS is 11 units. Where did I get PQ? PQ is the last one. Okay, one more type of problem we have to do. One more type of problem. I'm going to use Desmos to kind of visualize this for you. I gave you one with like training wheels here where I wrote out the 3 steps, and then we'll try one without. I don't know if we'll get to both today. We'll probably just get through the first one. It says, write an equation of the perpendicular bisector of the segment with these endpoints. Okay, I'm going to graph these on Desmos. We have an endpoint at -2, 3. And what was the other one? 4, 1. Okay. So here's my segment. I'm just going to draw it in for you. Doing my best here. We want to find the equation of the line of the perpendicular bisector of this segment. So the first thing we're going to do is we're going to find the midpoint, because we know that's where it bisects my line, right? So we're going to find where the midpoint is. We know how to do that. Midpoint formula. We find halfway between the x's, halfway between the y's. So let's do that algebraically with this case. So -2 plus 4, find the halfway of there, average that. 3 plus 1, average that. Okay, we get the midpoint to be 1, 2. 1, 2. Should I plot that on Desmos and see if it makes sense? Yeah, let's do it. 1, 2. Oops. Whoa! Did you see my marker, how close I was to the real midpoint? Did you see that, my guess, versus where it actually was? I was like right on. Aren't you impressed?
Yeah.
I just guessed. Just
Good
kidding.
job.
I knew what the point was.
You're a cheater.
Not as impressive, huh? I did this problem last class. Okay. The next thing we're going to do. Now, you might think we have to find the equation of this line. We actually don't. All we need to do is find the slope of this line. And since we know these lines are perpendicular, then we can figure out the slope of this line. All right, so that's the next step here. It says find the slope of the two given points. So here's your slope formula. Change in y over change in x. All right, so you got 3 minus 1 over negative 2 minus 4. I get negative 1/3. Was that a negative line? Negative sloping line? Oh, yeah, it was. What did I think it was? Okay, negative 1/3. That's the slope of this line. So let me ask you this. If we're trying to find the equation of the perpendicular line, what would the slope of the perpendicular line be? Oh, nice. Who said that? Walker?
Yeah.
Why do I feel like you're lying? Was it Ali?
No.
I heard somebody call you Alibo or something like
Yeah.
that. Can I call you that?
Yeah, go ahead.
Okay. Was it you?
Yeah.
How'd you get that?
Made it opposite
And?
and
Change the sign.
That's
changed the
opposite.
sign. Yeah, I don't know what the word is.
Reciprocal.
Reciprocals. Perpendicular lines have opposite reciprocal slopes, right? All right, so we know the slope of our line is 3, and we know it passes through the midpoint, 1, 2. Do you remember how to write equations of lines? Y minus y1 equals mx minus x1. Throw back. We know the slope is 3, and we know the point is 1, 2. Okay, let's put this into slope-intercept form. Distribute the 3. Add over the 2. That would be the equation of the line that's a perpendicular bisector. Should we do it on Desmos and see if that looks legit?
I mean, it's gonna be.
See if my line was a close estimate. Ooh,
Oh, you were off.
I was way off. Embarrassing.
I thought you did this.
All right, so there you have it, folks. Let's save the other one for tomorrow because I did the same thing as over there. And that looks like they'd be perpendicular, right? Those look like they form a right angle. Okay, that's a good start on 5.1. Thanks for watching.
Good job, Walker. You are the smartest person.